Chapter 4, Section 2 is about the sound intensity. So when it says intensity, it is very similar to density. And if some quantities are very close to each other, so intensity is high. If the quantities are farther from each other, so intensity becomes low. So sound intensity, in fact, completely related to volume. Yani, when what you hear from a sound source is normally called volume. So in physics we say it is the sound intensity. Before studying the sound intensity, first we should determine some terms. One of them is what power is. So the rate at which energy transferred is called power. This is the definition of the power. In the 11th class also you define this definition the same as this. The rate at which energy is transferred. Energy is transferred from one place to another. When it says the rate, you are going to divide it by time. Yani energy transfer rate is called power, or energy transferred energy divided by time. It's the power of that source. So SI unit of power is watt, and symbol is P. As you see, this is the equation for power. So then, if power is given in this section, sound intensity must be somehow related to power. Yes, it is related to power, because when you use a low power speaker, sound intensity will be low. If you use a high power intensity, sound intensity, what you hear will be high. So for that reason, so power is the center of our discussion. So then let's define it, what the wave intensity or sound intensity is. The energy transfer rate, and this is the power of a plane wave through a unit area is called wave intensity. So when it says a unit area, you are going to understand that you are going to divide power by area, and power divided by area along this power is distributed is called sound intensity or wave intensity. So it has a unit of watt per meter square. Yeah, is it like this? Yes, power is watt, area is meter square, so it becomes watt per meter squared. So in spherical wave, energy propagates equally in all directions. Why spherical wave? Because sound travels in the space in two-dimensional, like a sphere, on a sphere, as you see right here. So here is a source. The source produces a sound. This sound travels in all directions, up, down, right, left, back, forth, and so in all directions this sound expands. So when you combine all these points, which is expansion points, you are going to obtain a sphere. For that reason, in spherical wave it's said energy propagates equally in all directions. Thus the power emitted by the source is distributed over a spherical surface. Yes. Now initially say that here is the speaker. As soon as speaker starts producing sound, initial sphere is small. So then area of that sphere will be, of course, smaller. But as the sound expands, this spherical area increases. And the same amount of sound now will be distributed over a larger area. As the area increases, of course, the intensity of the energy or the sound on the area will decrease. You can also compare this to the light. For example, when you hold a flashlight at a surface which is closer, so you are going to see that light intensity on the surface is high. But when you take the surface far from the source, sound intensity will be light intensity will be smaller. Why? Because the light will distribute over a larger area. If light distributes or sound distributes over a larger area, its intensity will decrease. So then, if the sound is expanding over a spherical surface, instead of area, we are going to write the area of a sphere. So area of a spherical shell is 4 pi r squared. Then we are going to write in the equation sound intensity or wave intensity will be power divided by 4 pi r squared. This equation shows how the intensity of the sound wave decreases as distance from the source r increases. This occurs because the same amount of energy is spread over a larger area. Now, initial area is just small, that area becomes larger, and then much larger. So for that reason, sound intensity decreases as you move away from the source. Now, let's solve a problem. First sample problem 1. It says that What is the intensity of sound? Yani calculate I, questions calculating I, where a sound wave is produced by a trumpet at a distance of 3.2 meters. So distance to the source is 3.2 meters, which is the radius, of course, in this equation. When the power output of the trumpet, so trumpet produces a power which is equal to 20 watt. So the equation for calculating wave intensity is I is equal to power divided by 4 pi r squared. Power is given, 4 pi r is given, so you are going to calculate the answer as 0.60 watt per meter square. Next question is a practice problem. It says that at a maximum level of loudness, the power output of 75 pieces orchestra radiated as a sound is 70 watt. So 70 pieces orchestra means there are 75 pieces of instruments in this orchestra. All together they produce a power which is 70 watt. So what is the intensity of this sound wave? So questions calculate the sound intensity. To a listener, where is this listener who is sitting 25 meters from the orchestra, yani 25 meters away from the orchestra. So we are going to calculate. So equation is very easy. It's power divided by 4 pi r squared. So simply you are going to write that power is 70. So 4 pi 3.14 r squared, r is 25 squared. When you do the calculation, you are going to calculate the result. You are going to find the result. Next question is another question, very simple. If the intensity of the person's voice is 4.6 times 10 to the power minus 10 to the power minus 7 watt per meter square at a distance of 2 meters. So distance is given as 2 meters. At this distance, we are going to hear that sound intensity as 4.6 times 10 to the power of minus 7 watt per meter square. So by looking at the unit also you can understand which quantity is this sound intensity. So how much sound power does that person generate? Calculate the power. So again use the same equation. I is equal to power divided by 4 pi r squared. Because you are going to calculate the power, close multiply them. Power becomes I times 4 pi r squared. So then you are going to multiply them all. I is given 4.6 times 10 to the power of minus 7. So 4 pi is 3.14 multiplied by r. R is equal to 2 meters square of 2. This multiplication, the result, you are going to use the calculator and find the result. Now, we know that frequency is one factor in determining which sound is audible. Yes, if the frequency of a sound is between 20 Hertz and 20,000 Hertz, we can say that this sound is audible. But this is not the only condition to make the sound audible. Intensity is another factor in determining whether a sound is audible or not. So this is really practical to understand, because in your classroom, if your friends shout at you, you can hear him or her, but if whispers to you from a long distance, you cannot hear him. So even they sound with the same frequency. For that is an intensity, and the volume is also important to make a sound audible. For that is when we are explaining the audibility, we are going to use a graph. In this graph, so both factors will be there. One of them is the frequency. Another one is the intensity. So intensity and frequency are two factors which determines the audibility. So now when you look at here, you are going to see a graph. Now I'm going to explain this graph. Before that, so you should understand what softest sound means. Softest sound is low intense sound. As you see, 10 to the power minus 12 it starts. Loudest sound is the more intense sound, and volume is high. It is 1 watt per meter squared. This is the unit of sound intensity. So what does this graph represent? This graph represents that if a sound is inside this region, so this sound is audible. What does it mean? For example, think that normally we learned in the first section, 100 Hertz sound is an inaudible region according to that definition. However, this sound is audible only if its sound intensity is somewhere here. Yani if it is 10 to the power minus 10, 10 to the power minus 8, it's 10 to the power of, say, minus 9. If sound intensity of that frequency is greater than this number, so then we can say that this sound is audible. If lower than that, for example, assume that you produce a sound which is 100 hertz at an intensity of 10 to the power minus 10, so this sound is not audible because it is not inside that region. So the point must be inside this closed region. Then we can say that this sound is audible. Let's choose another audible sound, for example, 200 hertz. If you make a sound at 200 at an intensity of 10 to the power minus 8, say yes, because this point is inside this region, so this sound is audible. Or that sound is audible. Or this one is audible. So you can make the audible sound inside this region. But the smallest intensity which makes a sound audible is called threshold of hearing. So threshold of hearing is the lowest sound intensity. For example, look at here. At 1000 hertz, 1 kilohertz means 1000 hertz. The minimum intensity to make the sound audible is 10 to the power of minus 12 watt per meter square. Yani then we can say that threshold hearing for a sound at 1000 hertz is 10 to the power of minus 12. But for different frequencies, so, this threshold of hearing changes. For example, at 200 it becomes 10 to the power minus 10. At 50 it becomes 10 to the power of minus 7. At 20 it becomes 10 to the power of nearly 10 to the power minus 1. And so at 10,000 it changes. At 15,000 it is another number. So every different frequency has a different number for threshold of hearing. But generally we people talk on this interval, yani the middle of the spectrum, yani between 500 and 5,000. Between here we can talk, we can hear. Generally the sound around us is about this region. For that reason we are going to define the threshold of hearing as like this. The softest sounds that can be heard by an average human ear occurs at a frequency of 1000 hertz and at an intensity of 10 to the power minus 12. From now on, if I say what is the threshold of hearing at 1000 hertz, it is 10 to the power minus 12 watt per meter square. So the threshold of hearing at each frequency is represented by the lowest blue curve. Now I just showed it. This curve represents the threshold of hearing, which is the minimum intensity to make a sound audible. But when you look at the graph carefully, you are going to see that there is another line, which is the red line. This red line is the maximum intensity. So if the sound intensity is greater than that number, that line, so you can damage your ear. So the loudest sound that human ear can tolerate have an intensity of about 1 watt per meter square. As you see, this is a little changing. So as the frequency changes, the loudest threshold of hearing, which is called, is changing very little. For that reason, we can say that on average, this is nearly the same number, 10 to the power of 1 watt per meter square. So the loudest sound that human ear can tolerate have an intensity of 1 watt per meter square. This is known as the threshold of pain. The highest curve this red curve represents the threshold of pain at each frequency. So then if you expose your ear to sound above the threshold of pain, if it is above the threshold of pain, so it can cause immediate damage to ear even if no pain is felt. And you cannot understand, suddenly you can be a deaf person if your ear is exposed to sound greater than 1 watt per meter square. However, prolonged exposure to sounds lower intensities can also damage your ear. For example, you went to a concert, you are listening to rock music, but you are listening at a lower intensity than 1 watt per meter square, but it takes a longer time, 5 hours, 6 hours, 7 hours. This also can damage your hearing. For that reason, many rock musicians wear earplugs during their performance to decrease this sound intensity which is arriving their ears. Sound intensity is this, but now one more thing we should learn. It is the relative intensity or decibel level. So now when sound intensity doubles, the relative intensity does not double. What does relative intensity mean? Relative intensity is we can say that perceived loudness. Yani if the sound intensity doubles, our ear is not affected twice. Yani it also increases the sound, the perceived loudness also increases, but not directly proportional. For that, as we say that intensity of a wave determines the perceived loudness, but it is not directly proportional to intensity. Yani relative intensity or decibel level or perceived loudness is not proportional to sound intensity. If sound intensity doubles, perceived loudness or the relative intensity is not doubling. Why? Because your human ear is created in such form. For example, a sound twice the intensity of a faintest audible sound, and if you double the intensity of sound, it is not perceived twice as loud. Yani loudness does not perceived by 2 times. It increases but a little. This is because the sensation of the loudness is approximately logarithmic in the human ear. Yani what does it mean? Increasing sound intensity does not make the perceived loudness to increase. It all a little increases but not proportional. Relative intensity or decibel level, which is beta, is the ratio of the intensity of a given sound to wave to intensity at the threshold of hearing. It is measured in dimensionless. It is measured in dimensionless unit called decibel. So, equation for calculating the sound intensity, relative intensity or decibel level is this. Beta, which is the relative intensity, is equal to 10 logarithm I over IO. So I is the sound intensity at that medium. IO, you know, it is the threshold of hearing 10 to the power minus 12. So by using this equation, you can calculate the decibel level or relative intensity. For example, the intensity at the threshold of hearing 10 to the power minus 12 taken as a standard of its density, which corresponds to 0 decibel. In fact, when you write the equation here, you can get it. Beta is equal to 10 logarithm I over IO. So I, we said that it is 10 to the power minus 12. So IO also 10 to the power minus 12. So when you do that's 10 logarithm 1. So logarithm 1 is 0. For that, it becomes 0 decibel. So at the threshold of hearing, the sound intensity is 0 decibel. For example, let's calculate the sound intensity is threshold of pain. It is 10 to 1 watt per meter square. So for that, we are going to write in this equation, instead of I, 1. Threshold of hearing is 10 to the power minus 12. So when you divide this, it becomes 10 to the power plus 12. Get plus 12 in front of the logarithmic equation, multiply them 10 times 12, which becomes 120 decibel. So at threshold of pain, so sound intensity is 120 decibel. It is the loudest sound which a human ear can handle or tolerate. Let's solve another example. If the decibel level is 30 decibel, calculate the sound intensity I. So equation is beta is equal to 10 logarithm I over IO. So sound intensity, this decibel level is given as 30, so this is 30. 10 logarithm, we will calculate IO is 10 to the power minus 12. Divide by 10, so 3 becomes logarithm I over IO. So after that, we know that here is the base is 10. 10 to the power of 3 becomes I over IO. IO is 10 to the power minus 12. Cross multiply them, calculate the sound intensity. 10 to the power minus 3 times 10 to the power minus 12, which becomes 10 to the power of minus 9 watt per meter square. Another decibel level. If the decibel level is 6 decibel, calculate the sound intensity I. So again, 6 is equal to 10 logarithm I over IO. This is another one. So divide by 10 again. Divide by 10, get 10 logarithm I over IO. So here is base 10. Square of power 10 to the power of 6 is equal to I over 10 to the power minus 12. Cross multiply them. So calculate the sound intensity as 10 to the power of minus 6. But questions are generally not in this form. They are asked in another form, like this. It says, when the decibel level of a traffic in the street goes from 30 decibel to 60 decibel, how much greater is the intensity of the noise? Yani compare the final and initial sound intensity it asks. This is a ministry exam question, 2014 and 15. So initially it is 30 decibel. So for that I'm going to write beta initial is 30 decibel. Finally it goes to 60 decibel. Final is equal to 60 decibel. So we're going to calculate the relative sound intensity for initial and final. For the final, remember we got the for 60 decibel, it is equal to 10 to the power of 6 times 10 to the power minus 12. We just write it 10 to the power 6 times 10 to the power minus 12. For 30 decibel, the first one we did it, it is 10 to the power of 3 times 10 to the power minus 12, 10 to the power of 3 times 10 to the power minus 12. So then compare how much greater means compare them. Compare means divide them. When we divide them, 10 to the power minus 12 cancels. For that reason, final sound intensity divided by initial sound intensity is 10 to the power of 6 divided by 10 to the power of 3. When you look at the equation, you see that this is 6, that is also 6. This is 3, this is also 3. So without doing this calculation, you can directly take 6 here, you can directly take 3 here, 10 to the power of 6 divided by 10 to the power of 3, 10 to the power of 3, and 1000. So which means the sound intensity of noise increases by a factor of 1000. You can do the equations in the same manner as well. For example, this is another equation, 2013 and 2014 year, it's asked. When the decibel level of traffic in the street goes from 30 decibel to 50 decibel, how much greater is the intensity of the noise? So initially it is 30, it goes from 30 to 50, so finally it is 50. So we will compare the final sound intensity to initial. So again do the same, 10 to the power of 5 divided by 10 to the power of 3, it becomes 10 to the power of 2, which is 100. So intensity of noise increases by a factor of 100. We can say this. Now let's solve a conceptual challenge question. This is another question. Maybe it's a little hard to understand and try to concentrate. It says that federal regulations require that no office or factory worker can be exposed to noise levels, which is noise levels, remember it is decibel level, that average above 90 decibel for 8 hours a day. And in 8 hours, if you are starting, you are working in a factory, so the noise level or decibel level or relative intensity of that factory cannot be greater than 90 decibel. Does a factory that currently averages 100 decibel. So a factory right now is producing a sound which is 100 decibel. As you see, this is greater than that number. So this is the initial condition. Must be reduced its noise level by 10 decibel. So from 100, this factory must decrease the sound relative intensity to 90. For that reason, I'm going to say that initially it's doing something wrong, producing a high intense sound, which is 100 decibel, but according to law, it must decrease that sound intensity to by 10, maximum it could be 90 decibel. So assuming that each piece of machinery produces the same amount of noise, yes, the machine produces the sound. If there is one machine, it produces sound intensity 1. If there are 2 machines, sound intensity doubles. If there are 3 machines, sound intensity triples, and so on. Yeah, number of working machine, running machine is proportional to ratio of the produced sound. So we will calculate how much is the sound intensity ratio of the sound intensity changes in this case. So then we are going to get the number of machines which are working initially and finally. So now it is 9. Just write it here, 9. This is 10 to the power of. Then this ratio is 1 over 10. What does it mean? Now question is asking about the percentage. What percent? So it's not giving a number. Now from ratio we can read the percentage. For example, if initially there are 10, sound intensity is 10, finally sound intensity will be 1. Yeah, and sound intensity will decrease by from 10 to 1. But percentage means, if you should write it as percentage, multiply by 10 to make it 100, because percentage is expressed in terms of 100, so it becomes 10 over 100. So if initially sound intensity is 100, final sound intensity is 10. So then, because the machines produces that sound, so we can say that number of percentage of the sound also decreases from 100 to 10. Number of machines which are working also must decrease from 100 to 10. So then initially if there were 100 machines working, finally 10 machines are working, so 100 minus 10, 90 machines must be switched off to removed. Then 90% of the machines must be switched off to decrease the sound intensity from 100 to 90. In fact, this is general for all cases. If in general, you can say like this: if you want to decrease the decibel level 10 by a number of 10, and 10 decibel decrease in relative sound intensity corresponds 90% of the all initial sound sources to be switched off or removed. If you wanted 20 decibel decrease in the relative sound intensity, it corresponds to 99% of all initial sound sources to be switched off. If 30 decibel decrease you want to do in this sound intensity, in this case 99.9% of all initial sound sources must be switched off, and it goes on like this. Force vibration and resonance is the next title. So there are 1, 2, 3, 4 pendulums. 2 of them are in equal length, others are at different length. So if the length of the pendulums are equal, so then we can say that the periods of vibrations or frequency of the vibrations are equal. But if the lengths are different, so the period of vibrations or frequency of the vibrations are different. So now when we set this one of these pendulum into motion, for example, you set this one into vibration, its vibration is transferred through this string or through this pipe to others. So others also starting to vibrate by time. So this type of vibrations are called force vibration. And this one, which is set in vibration, forces other pendulums to vibrate. For that reason, these vibrations are called force vibration. The force vibration is not only for pendulums. For example, you can see the force vibration in vibrating strings of a guitar too. So we are going to hit the string of the guitar. So guitar string will start to vibrate. So it will force the bridge of the guitar to vibrate too. So the bridge also starting to vibrate. This bridge is connected to the body of the guitar, body is starting to vibrate. So this chain of vibration is called sympathetic vibration. So first string vibrates, later the bridge vibrates, after that the guitar body starts to vibrate. So this is called sympathetic vibration. This chain of the vibrations, forced vibrations, are called sympathetic vibrations. Why do we use is it important? Because if you use only the string of the guitar, so less number of molecules are in contact with the string of the guitar. For that, as in sound intensity, and vibration is number of vibrations transmitted to the air is very small. For that reason, the energy of the wave, the intensity of the wave will be small. But if you set up the body of the guitar into vibration too, because the body is so large in area and so many molecules are in contact with the area of the guitar body, so many molecules of air start to vibrate, then this increases the sound intensity, which is heard by the listeners. Another title is a kind of force vibrations, the resonance. For every oscillator will vibrate at a certain frequency. Yes, everything is vibrating with a certain frequency known as its natural frequency. If the natural frequency of two oscillators or two oscillating systems are equal, we say that these systems are in resonance. Why is it so important? Because such a system, energy can be transferred from one of them to another one. So now let me go back to these pendulums. Now look at here, the pendulums, two of them are in equal length. And the natural frequency of these two are equal. When we set this pendulum into motion, it will be observed sometime later. All three will start to vibrate, but these two will stop sometime later. But the second one, the middle one, will continue vibrating because these two have the same natural frequencies because they have the same length. So then what will happen? These two will continuously transfer the energy from left to right, right to left, left to right, because these two are in resonance, because their natural frequencies are equal. Another striking example for resonance is occurred in 1940 when the Tacoma Bridge collapses in Washington. So this bridge is normally oscillating like this. Everything is oscillating, but this bridge is a little extraordinary. It was oscillating with a greater amplitude. But when the high winds start to blow, because the wind started to add energy to the system, to the bridge, because the energy is proportional to amplitude. As energy increased, amplitude of the oscillation started to increase. Finally, this bridge collapses. It is because of what the resonance between the wind and the bridge. Now let's answer the sectional questions. Question number 1: when the decibel level of a traffic in the street goes from 60 to 40 to 60 decibel, how much greater is the intensity of noise? Remember, intensity of noise, to compare them, we should compare the sound intensity. Initially, the decibel level is 40, finally it becomes 60. So we will find I2 over I1 final divided by initial in sound intensities. The Heck method is 10 to the power of 6 divided by 10 to the power of 4. It is 100. So intensity has increased by a factor of 100. A tuning fork consists of two metal prongs that vibrate at a single frequency and when struck loudly. What will happen if a vibrating tuning fork is placed near another tuning fork of the same frequency? Explain. Because they have the same natural frequencies, the first one starts to vibrate because, like the pendulum, second tuning fork also starts to vibrate because it picks up the energy from the first one because they are in resonance. Question number 3: which of the following factors change when the sound gets louder? Louder sounds means high intense sound. So intensity gets louder. Decibel level also increases. Amplitude also increases. But pitch is related to frequency. When pitch gets higher, frequency increases. If frequency increases, wavelength decreases because speed of the sound is constant at that medium.